Well, the previous lesson was finished with the definition of filtered category, as I remember, yes, and filtered calimit, yes. It's calimit of a functor from a small filtered category to somewhere. So let us first recall that if we have a small category, some functor, let us say A, from this category to the category of modules, then there exists calimit of this functor, and it can be computed as a co-kernel of some concrete map. Like take the direct sum of AI for O phi from I to j. Like here, the direct sum for all morphisms of j. And we take for each morphism the domain of a morphism to the direct sum of AI for I simply object of j. And here the map is the following. If you have like A in component phi, how to denote it, like A phi. So it is some A in component phi, phi is from I to j, and all other components are 0. Then it goes to A in component I minus minus phi of A in component j. Yes. And the kernel of this map, what is denoted by f, for example. This is map by pi. It is calimit of sorry, key A5. The image of phi and the functor A. So if you have, for example, short exact sequences AI, BI, CI, yes, for all I in J, and for phi from I to j, you have a sorry, you have a morphism of short exact sequences let's write I, j, here a phi, b phi, c phi. Then you have a colimit sequence. Yes. Colim A, colim B, colim C. And now you can put the sequence in the following diagram, commutative diagram. Sum of AI for I from opt j, here some bi for I from op j, some ci from op j. Here you have, of course, short exact sequence. Here the maps pi, and then you have here some I for phi I to j, some bi for phi I to j, of ci j. Here you have what you have, like some maps. Yes, in fact we don't need this part above. So these maps are epimorphisms. So we can apply snake lemma, and snake lemma tells us that here this sequence is exact. So here you have epimorphism, and here the kernel is equal to the image. In general, you don't have monomorphism here, of course, but our aim is to prove that for filtered colimits you have. And to prove this, we will need the following technical lemma. Let J be a filtered category. A is a functor from J to mod R. Then two conditions hold. First condition is that any element of colim of A is of the form pi of A for some A I Okay. So if the limit is filtered, then any element here is an image of under pi of some element from some component, not from the direct sum. And the second is that the kernel of the map from AI to Kalim of A is equal to the union of kernels the fact that this lies here is more or less clear, and here we will have to prove that if some element from AI goes to 0, then there is some phi such that a phi of this element is 0. The first part is quite easy. Let we have some element of in the limit, then it is of the form pi of AI where AI is 0 for almost all I. So only a finite number of non-zero i's, and for this i's we can choose j such that there exists phi I from I to j for any I such that AI is non-zero. So in this case, pi of AI is equal to pi of I minus A I so it's a component. Sorry. Sum of A phi I lies in component J plus pi of And by definition of pi, this one is 0. So pi of I lies in pi of aj. And it is what we want to prove, that there is some index that for any element there is some index such that this element lies in the image of
what
aj.
is sigma of A? Or is the sum of?
It's sum. The second part is not difficult, but well, it's not very intelligent, but it's more difficult in the technical, from a technical point of view. So let us take some element in AI that goes to 0. So pi of A is 0. Then there are some ck such that A is equal to well, here A is in AI, yes, such that A component I is equal to the sum of ck component ik minus ck and some data from A ik and some phi k from ik to jk minus A phi k of ck in component jk. So now we want to put this in some convenient form to prove that what we want. Well, first of all, there is some, so there is finite number of ck, yes, and hence there is some j such that there are morphisms from jk to j and from I to j. Yes. So first of all, we can assume that I equals to j. Why? Because we can like, let us denote this by phi. Yes. Then we have phi of A. The component j is equal to the sum, the same sum as here, k minus A k of ck and here minus a component I minus a phi a component j. So we can substitute a by a phi of a and prove for a phi of a that it lies in the kernel of some map, and it will imply the same assertion for a, of course, because the composition will annihilate a. And for a phi of a we have this quality, so everything is okay. So we may assume that I equals to j, etc. That there are morphisms from jk to I, more or less. This one to prove, so then we may assume that that jk equals to j. Why? Because since we have some psi k from jk to j, then we may we may take the expression ck minus a phi k of ck, this end component ik jk, yes, and substituted by the following expression ck k minus a ck phi k k, and this will in the component j minus a phi k ck, it's in the component j k minus the same thing as here, but we will write it as a psi k a phi k ck, the component j, yes. So we can replace this expression by two these expressions where that correspond to some maps. This correspond to a map from ik to j, and this to a map from jk to j. So when we replace everything, we may assume that initially jk is equal to j. So what do we have? We have a I equals to sum of ck in the ik component minus a phi k ck in the I component for some ck from a ik, and phi k from ik to I. What now? Suppose now that there is some k such that ik is equal to I. Then this guy lies in, so it's in component I, k minus k5k k I. It lies in the kernel of a gamma for some gamma from I to I prime. Because by the definition of a filtered category, there is some gamma from I to I prime, such that equalize two arrows. So one arrow is ID from I to I, and another one is phi k. So gamma such that gamma equals to gamma phi k, and then it is what we need. And one can note that if you have some element like b in the component ai, and b equals to b prime plus b to prime, and b prime lies in the kernel of b phi, b2 prime lies in the kernel of psi, then we first can choose beta such that choose like let phi be from I to j prime, psi be from I to j2 prime. Then we can choose some j with two morphisms. Beta prime and beta 2 prime. Then we will obtain that b prime lies in the kernel of a beta prime phi, b2 prime lies in the kernel of a beta 2 prime psi. And then, since beta prime phi and beta 2 prime psi both start at I and finish at j, then there is some delta such that delta beta prime phi equals to delta beta prime psi, and then B lies in the kernel of A delta beta prime phi, which is the same as kernel of A delta beta 2 prime psi. So if we have some element that is already lies in the kernel of some A phi, we can subtract it from our A, and it will not change anything. Because of this, since this guy lies in the kernel of A gamma for some gamma, we may simply cancel it. So we may assume that that ik is not equal to I for all k. Yes. Now the only problem that we have is that probably we have some ik and il that are not equal. Suppose that ik equals to il, but phi k is not equal to phi l. If phi l is equal to phi k, we simply can replace like ck and cl by their sum. But in this case, there is gamma such that from I to j, such that gamma phi k equals to gamma phi l. Yes. Then we can replace the sum ck minus a phi k of ck by the following sum. We can replace it by, let it be here L and T, for example. By what we can replace it? By the sum ck minus a gamma phi k of ck yes, plus minus the sum a phi k of ck minus a gamma of some a k of ck. So we replace I by j now, and here we have two equal maps, so we can decrease the number of coinciding indices, because here the index is I. Yes, here j, k, j, and so I is not equal to ik, so this guy doesn't give any incrimination of equal indices. Have to replace also a by a gamma of a, yes, because like it was a and a was in component I, but we want it to be in component j, so you can write that gamma of a equals to this guy, but here we have to add a, and here we have to add a. To not interrupt our conditions. So in final we have for a, not for a, but for some map, we have that a phi of a equals to sum of ck minus here component I, a phi k of k in component I, and we now have that all ik are different and not equal to I. So for any k, on the left in the component ik we have 0. Okay. On the left ik component is 0, and on the right ik component is ck. So ck is equal to 0 for all k. And hence a phi of a is 0. Well, it would be much easier that if we assumed that between any two objects there is only one morphism, but in general it's not very difficult too, but quite technical. So when the lemma is proved, assume that here in this diagram our category J is filtered. Well, suppose that J is filtered. Let us take some element here that goes to 0. Yes, this element by our lemma is pi of a. it comes from A here, of course. Sorry, not here, in the colimit. We have here A, pi of A, that goes to 0. By our lemma, it comes from some A, yes, and A lies in AI. Then here we have alpha I of A, and it goes to 0. So, and this alpha I of A lies in BI, yes. And moreover, pi of alpha I of A equals to 0. So, by our lemma, there exists some phi, yes, from I to j, such that A phi alpha I of A is 0. Yes. But we know that by our assumption, A phi like alpha and beta define a natural transformation from B phi from A phi to B phi. So in fact, the same thing is alpha j sorry, 1 second. Alpha j A phi of A. Yes, and since alpha j is mono, we have A phi of A is 0, and hence pi of A is 0. So, what we have proved is that filtered colimit is exact. If we have a filtered colimit of short exact sequences, then we have a short exact sequences. Short exact sequence. So now we are ready to prove one important theorem that allows to deal with stores of arbitrary modules using finitely generated modules. The theorem is the following. Suppose that we have a right exact functor f. That commutes filtered colimits and such that any filtered limit of projective modules is f acyclic. Then ln f yes, ln f of colim A, where A is a functor from a small filtered category to mod A, is isomorphic to colim and f So in this case, left-right functors of f commute with filtered colimits too. Proof. So we have some AI, yes, for I are objects of J. And we want, our plan is to choose projective resolutions of AI for all I and lift the maps phi, the morphism of J, yes, the images of morphisms from J to these resolutions in such a way that we will have a functor from J to complexes, like we want to construct resolutions we can do this in some way, but we want to construct them in such a way that afterwards we will lift maps a phi from I to J to resolutions. Yes, like phi 1, 0, phi 1, phi 2, so on. But we want to lift them in such way that we will be able to calculate colimit in each component. For this, we have to obtain functors. Yes. So this means that if you have also some aj k, and some psi from j to k, and we have projective resolution of ak, then we can take our lifts of a psi. Yes. And also we can take the composition of phi and psi. Yes, here we have a psi phi. And take the lift of this map. So here we obtain a phi psi phi 0 a psi phi 1 and so on. And we want like this composition to be equal to this composition, and it is of course not true automatically. We only know automatically that if we take all these compositions, take the difference, then we will obtain a zero homotopic map, because one composition lifts this, another this, and they are equal. Yes, but we want them to be strictly equal, not modulo some homotopy or something like this. So we have to construct everything in such a way, in some tricky way. So we have, for example, a, I, and we take P0 I, not some arbitrary projective module, but we take P0 I to be a free module on all elements of AI. Yes. So, and with the obvious map from it to AI, like of course here, if we have epsilon, then epsilon of 1 in the component A goes to A. And then we can lift our maps, yes, because if you have some I to aj, here we have P0I, P0j, here we have A phi from I to j. Then here we can construct A phi 0 in an obvious way. We simply define A phi 0 of 1 in component A to be 1 in the component A phi phi. Yes. So we simply send a generator here to the corresponding generator here that corresponds under A phi. So we simply apply a phi to indices or generators. And so it's obvious that this square is commutative, yes. And also it's clear that in this case we have a psi 0 composition A phi 0 equals to k psi phi 0. So we obtain a functor. Then, of course, on kernels we have a unique map that makes the diagram commutative, and by the uniqueness the map on kernels will satisfy the analogous condition, so we can then proceed by induction. So for kernels we choose P1 I1 to be equal to R to free module generators indexed by the kernel, and the obvious projection on the kernel, and again you can lift this map between kernels to projective covers. So in final we have resolutions Pi, AI, and morphisms. Of complexes. A bullet from I to J phi from I to J that lift the phi and satisfy the functoriality condition. That a psi composition a phi equals to a psi phi as a map of complexes. Then we can take the K-limit complex. Then call in a bullet is a complex and by the exactness of filtered colimits the induced map from colim bullet to colim A. Let's call colim epsilon is a quasi-isomorphism. Well, by our assumptions of the theorem, this guy will be a f-acyclic resolution of the colimit. So we can use this resolution to compute the left-derived functors. We have
this colimit of A shouldn't be colimit of B. Equals epsilon. There was a map of
well. It is like a notation question. It is because of this notation that I put. Probably it would be better to put another notation, but like here, of course, A chi I is in fact B I k. So to compute the left-derived functor of the colimit, we need to apply f to this colimit and take the homology. So now by our assumption f commutes with colimits, so it's the same thing as homology of the colimit of f dot. But filtered colimits are exact, so it commutes with homology, because homology can be expressed in terms of short exact sequences. So it is colimit of h n f a dot, and this is exactly what we want. So now we want to apply this to torus. We know that tor is the left-derived functor of tensor product. So we want to show that, in this case, if f is the tensor product, then f acyclic, if it is tensor product with some concrete module, then it's not clear what is f acyclic, but for sure all flat modules are f acyclic. Yes, if f is a tensor product with something. So we need to show that filtered colimit of projective modules is flat. Yes. In fact, filtered colimit of flat modules is flat. So let us take some monomorphism. Then we know that suppose that AI is flat for all I. This means that X tensor over I, Y tensor over I is mono for any I. Well, so then, since filtered colimit is exact, then colimit of X tensor over A is still submodule of colim Y tensor over A. Yes. So this means that we apply first the functor and then functor A and then tensor product. But the tensor product commutes with colimits. It can be shown in the picture that with cokernels, yes, if we tensor it by something, then we still will have epimorphisms because tensor product is exact. So, in fact, this guy is isomorphic to X tensor over R column A, and this guy is morphic to Y tensor over R column A, and hence here we have mono, and hence A is flat. As a corollary, we see that if we have some functor from filtered category to mod R, then the Tor functor of the colimit of A and B is isomorphic to the colimit of Tor functors. Well, this guy, of course, means that you first apply A and then Tor R of B, which is simply Ln dash well, and I don't know if we will apply this at lectures, but we now can apply it at seminars and solve some problems that we still haven't solved. So next we will study the X functor, but before we study X functors we need to introduce injective modulus and prove some facts about them that we already have used but without proofs. So the next paragraph is X, and the zero part of it is injective modulus. So let we have a module M, then it is called injective, if, well, first the picture, if for any map from X to M, yes, and any mono from X to Y, we can construct a map from Y to M such that triangular triangle is commutative, let us say it f g, yes, f iota. If for any homomorphism f from x to m and any mono iota from x to y, there exists g from y to m such that g iota is f. So it's not difficult to see that m is injective if and only if for any mono iota from x to y, the map hom y m to hom m, here hom r to m is epi. Yes, it is exactly the definition that if you have monomorphism, then for any map from x to m, there is a map from y to m such that hom r I m of this map is exactly f. Another remark is that if mi is injective for all I in I, then the direct product of mi is injective. Okay. We will need this to prove that any module can be included in an injective module. The first thing that we will prove is the Bayer's criterion. That states that to understand if the module is injective or not, we don't need to check all injective, all monomorphisms. We only need to check some concrete monomorphisms, some monomorphism of some concrete form. So M is injective if and only if for any right ideal I of R and any module map, a module homomorphism I to m, there exists G from R to M, again a model homomorphism such that the triangle I R F G commutes. Well, in one direction, this if and only if is absolutely clear, because this condition exactly means that for y equals r, this condition holds. So if this condition holds for all y, then of course it holds for y equals r. So before we will prove this criterion, let us state some corollary. Let A be an abelian group. Then A is an injective Z module if and only if A is divisible. Divisible means that for any A and any non-zero integer n, there exists B from A such that n times B is A. Well, corollary is clear because to state that that A is injective, we need to be able to continue any map of any inclusion of ideal to Z, any map from some ideal of Z to A to Z, but any ideal of Z is Z. Yes, so if we have here a map of this form, then for any map from Z to A here, we have to have a map from Z to A here, such that this triangle commutes. But a map here, what is the map from Z to A? We have to map 1 somewhere. So if 1 goes to A here, here it goes to M. So M has to go somewhere to B, and it has to go to such B that M has to go to A, yes, under this map. But to define this map, we need to define it on 1. Yes, so 1 has to go on this G. Yes, G of 1 has to satisfy m times g of 1 to the g of m equals a. So if there is no b such that mb equals a, then such g cannot exist, and if there exists, then we simply can send 1 to this b and obtain g. Well, so even without Bayer's criterion, of course, it's clear that if some module, if some abelian group is an injective Z module, then the group is divisible. But only with Bayer's criterion we can prove that if a group is divisible, then it is injective as a Z module. If we hadn't Bayer's criterion, then it wouldn't be unclear how to prove about some group that it is injective, because it's difficult to consider all monomorphisms of abelian groups. So we think that we exactly have time to prove the Bayer's criterion. What we need to prove? We need to prove that any well, suppose that the condition on ideals is satisfied, so that if you have a map from I to M and I is an ideal in R, then there exists this. Suppose that this part is satisfied, and we want to prove that M is injective. So we have to take some mono from X to Y and F and homomorphism F from X to M, and prove that there exists G from Y to M that makes this triangle commute. Well, we will do this by using Thorne lemma. So let us consider the set of all intermediate submodules X prime between X and Y with let it be iota prime, iota 2 prime, with with maps F prime from X prime to M such that F prime iota prime is equal to That'd be iota prime and gamma prime is equal to f. So if we have two such elements, like we have x prime, y, m, here f prime, and we have x2 prime, y, here f2 prime, then x prime, f prime is less or equal than x2 prime, f2 prime if x prime lies in x2 prime, yes, and f2 prime on x prime is f prime. So if we have here an inclusion such that this one commutes and this one commutes. Yes. Well, it is clear that the set of such pairs x prime f prime satisfies the condition of Thorne's lemma. I don't remember the name of this condition, sorry. That any ascending chain has an upper bound. So there is maximal element Thorne's lemma implies that there exists maximal. So x lies in x prime, here we have f, and here some f prime. This guy commutes, and there is no intermediate x2 prime here to what we can extend f prime. We need to prove that x prime equals y. Suppose that it's not so. Then there exists some b in y which is not an x prime, and now we want to extend our f prime to a bigger submodule. Yes. Oh, I will look to be more fast. So let us consider J, which is a set of such R in R, that B times R lies in X prime. Yes. And it's clear that J is a right ideal of R. So we can construct a map. I don't know how it's called. It's called phi from J to M, defined by the equality phi of R equals to f prime of BR. Yes. And then let be phi prime. And then there exists phi from R to M such that phi on J is phi prime. Yes. It is what we assumed. And now we define x prime to be x2 prime to be x prime plus BR. Yes. And we define f2 prime from x2 prime to M by the equality f2 prime of A plus BR equals to what? Equals to f prime A plus phi of R. So it's clear that f2 prime on x prime is f prime, because if this guy is 0, then we simply obtain f prime of A. And it's not very difficult to check that f2 prime is well defined. It's like exercise. f2 prime is well defined. It is like one phrase, but we need to stop, I think. And hence we obtain contradiction to our assumption that x prime is maximal. That finishes the proof.